Hey everybody, in this video we're going to talk about rates of change, net change, and signed area under graphs. So we're going to start with a relatively simple question. A car travels down the highway at the constant velocity of 90 kilometers per hour. How far does the car travel in 3 hours? The key to this problem is we're talking about a constant velocity. And because of that, the calculation turns out to be a matter of simple algebra. We know the car's moving 90 kilometers per hour times 3 hours of motion, and that gives us 270 kilometers. And we'll notice even that the units agree, and so you can see how to get the total distance traveled just as a product of the rate times the time traveled. Similar kind of problem here. A drum leaks oil at a constant rate of 3 gallons per minute. How much oil leaks out of the drum in 12 minutes? The key fact here, again, is we're dealing with a constant rate. And because of that, we can take a simple product. 3 gallons per minute times 12 minutes gives us 36 gallons. And once again, we can check the units. 36 gallons, gallons being an amount of oil, which is what we would expect from this calculation. The deal here is that a constant rate of change problem basically turns into a simple algebra question. And we'd like to show that actually we can translate it into a simple geometry question as well. So imagine that we have time, and against time we're plotting the rate of change of some quantity. So it could be a car traveling down the road, in which case we'd be measuring time, say, in hours, and velocity, the rate of change in this case, could be kilometers per hour. Or maybe we're looking at oil leaking from a drum. We could be measuring time in minutes, and the rate of change of oil in the drum is being measured in gallons per minute. Let's be abstract about this. Our time units could be anything. Let's say they're called yombits. And suppose we're measuring the rate of change of some process where this rate of change is measured in boozles per yombit. We can still do a problem based on constant rate of change. If we say that the process is changing at a constant rate of k, and we want to look at a problem that starts at t equals a and finishes at t equals b, the change in time is going to be b minus a, and the rate of change is of course measured in change in boozles over change in yombits. So if you want the change in boozles, you should multiply k by the change in yombits, which is to say you get k times b minus a. What have we really done in this graph? K is the height of this graph, and b minus a is the width of this interval. And when you multiply them together, you're actually finding the area of a rectangle. And the area in this case, I should point out, is measured in boozles, because that's yombits times boozles per yombit. And so we're getting an area here. And that area is telling us a total change. So you can go back and see how this fits with the velocity of a car or the rate at which oil leaks from a drum. We're getting the same kind of process here. Every time we have a constant rate of change problem, we can do simple algebra to find the total change. So working with constant rates of change is easy, but what happens when we switch over to non-constant rates of change? Let's go back to our oil drum problem. Suppose the rate at which oil leaks from a drum varies according to some function r of t, and it's going to be graphed below. How much oil leaks from the drum from time 0 to time 12? Let's not solve this exactly. Instead, we're going to approximate the amount leaked by pretending the rate is constant on 4-minute intervals. So for example, on the time interval from 0 to 4, what we could do is pick out some representative rate that occurs during that interval, and that would be somewhere between 8 and 4.4 gallons per minute, say. So let's just pick something like 6.5, somewhere in the middle. So we'll just pretend like the oil was leaking from the drum at a constant rate of 6.5 gallons per minute over that time interval. And similarly, over the time interval from 4 to 8, we'll just pretend like it was leaking at a constant rate of 4 gallons per minute. And then finally, on the last interval from 8 to 12, we'll assume that the rate of leakage was 2 gallons per minute. So now we've broken this up into 3 constant rate problems. So the amount leaked would just be the area of the first rectangle plus the area of the second rectangle plus the area of the third rectangle for a grand total of 50. So our approximation turns out to be about 50 gallons. Well, we could repeat this process and we could use smaller intervals. Let's use 2-minute intervals this time. So this time we might take our representative rates to be respectively 7, 5, 4.5, 3, 3.5, and 1. And when we calculate the amount leaked, we're going to add up 6 contributions now over 2-minute intervals, and this time we get an approximate value of 48 gallons. So our approximation has changed, but presumably we're getting a better approximation because we have the ability to sample our rate of change function more often. Now we could use 24-second intervals, and you get a graph that would look something like this, and you can see that you've got a whole bunch of rectangles whose total area is starting to look more and more like the area under the curve. We could keep going with this, and it seems reasonable to assume that the actual amount of oil leaked is actually equal to the area under the graph of the rate function. So somehow if we could come up with this area right here, let's suppose it was about 48.36, well, that would be the very best approximation to the amount of oil that leaked out of the curve. And so that is our motivation for thinking about area as net change. So let Q be some quantity that is a function of time. So the amount Q changes as a function of t, time. And its rate of change function is, in Leibniz notation, dq dt. So suppose you actually calculate the graph of dq dt as a function of time. And you look at the time interval from, say, A to B. So here's the principle. Suppose we're interested in the net change in Q from t equals A to t equals B, which is to say we're interested in Q of B minus Q of A. That's the change in Q from time A to B. Well, it equals the area under the graph of the rate of change function dq dt from t equals A to t equals B. If we could find that area under the curve, we've found the difference Q of B minus Q of A. Until this point, we've only been looking at rates of change that are positive, but you could have negative rates of change. So how does that change the picture? Well, that's going to lead us to the notion of signed area. Imagine we have a car traveling down the road, and this is the positive x direction, so our mile markers are laid out in the direction of increasing to the right, and you have a car that's traveling along this road. And suppose we were able to plot the velocity in kilometers per hour as a function of time in hours, and say the velocity function looks something like this. Well, what's going on here? So for the first 2 hours, the velocity is positive. It's a positive rate of change, and that means our car is moving to the right. But then from hour 2 to 3, the velocity is now negative, which means the car is turned around and is moving the other direction. Once again, from t equals 0 to t equals 2, the motion is to the right. And then from time 2 to time 3, the motion is to the left. Now, what if we want the net change in position from time 0 to time 3? How would we calculate that? Another name for this quantity is called the displacement. Let's break this up into 2 parts. First of all, there's the motion to the right, and by looking at this polygonal area, we can calculate directly that the area under this velocity curve from time 0 to 2 is 95. So you know from hour 0 to 2, you go 95 kilometers to the right. Now you turn around and you move in the other direction. Now this area is 15, but we're moving to the left, so we have to subtract off 15 from our original 95 kilometers to the right, so the net displacement from time 0 to 3 was 80. Let's think about this in terms of areas. The net change in position, or displacement, turned out to be the distance to the right minus the distance traveled to the left, which is to say we're taking the area above the horizontal axis and we're subtracting off the area we found below the horizontal axis. This is going to be what we call the signed area between the horizontal axis and the graph, or just signed area for short. Let's say a little more about the definition of signed area. Suppose f is a continuous function. The signed area over the interval a to b between the graph of f and the horizontal axis is defined to be the area above the x-axis and below the graph of f, and then we subtract off the area trapped below the x-axis and above the graph of f. Let's look at an example. Here's a graph that consists of a quarter circle and then segments whose endpoints and centers and radius are all what they appear to be. Let's find the signed area from -6 to 6. So we're shooting for this decomposition. We want the area above, and then we want to subtract off the area below. We can think of the area below as being negative area if you like, so we're going to add this negative area. Now we can decompose this into simpler pieces. So there's a quarter circle, a rectangle, a triangle, another triangle, and another rectangle. Now that's perfectly reasonable, but let's try again, this time looking for symmetry to make our calculation easier. So the thing to notice here is that there are two regions that are congruent to each other, one appearing above the x-axis and the other appearing below the x-axis. So we don't even need to calculate the area of either of those because we know they're going to cancel each other. We could have, from the get-go, just looked at this region on the left, which is simply decomposed into a quarter circle and a rectangle. So we should have known immediately that the signed area was going to be about 10.069. Now let's look at an application in terms of net change. The signed area under the graph of the rate of change function dq dt on the interval a to b yields the net change of q over the same interval. Suppose T is the temperature of a room, and here is its derivative, in Leibniz notation, derivative of temperature with respect to time, and we're measuring the rate of change of temperature in degrees Celsius per hour. Now suppose we graph this rate of change function of temperature, and we want to estimate the net change in temperature from t equals 0 to t equals 6. Let's make sure we understand what's going on here. For the first hour, the temperature is actually increasing because the derivative function is positive. And then from hour 1 to 4.5, the temperature decreases because the derivative is now negative. And then finally, the temperature increases again from time 4.5 to 6. The question now is, what is the net change? Now, we could calculate a lot of polygonal areas here, or we could start looking for some cancellations. For example, we could imagine that these two regions are roughly the same. They should cancel. Here are two regions that cancel. Here are two regions that cancel. Here again, a region that cancels. Here are two more regions that cancel, and those regions cancel. Lo and behold, we don't have to make a single calculation, and we realize that what we're saying is the temperature at time 6 minus the temperature at time 0 is about 0. Or if you want to put it another way, the temperature at time 6 is roughly the same as the temperature at time 0.